everybody. We're going to start with the second introduction to Gaussian processes, and we have Richard Wilkinson, who is a professor in the School of Mathematics and Statistics here at Sheffield.
Thank you. Well, thank you for coming, everybody. It's really nice to see so many people again. So I thought what I'd do is basically repeat what Neil said, but slightly more maths, or as Neil put it, to make it harder to follow by just putting in more detail. And I know I've got too much text on the slides, and in part that's because there was no whiteboard when I arrived this morning, so I've been adding in algebra frantically, but now there's a whiteboard, so they're a bit cluttered. But what we're going to do is basically look at reasons why you might want to use Gaussian processes, and in some places just work through some of the kind of derivations, just 'cause I think it's interesting to see it once or twice. Okay, so first of all, what are Gaussian processes? Well, they're just a particular choice of stochastic process. So what's a stochastic process? So it's just some collection of random variables, f, say, that's indexed by some index, which I'm calling x here. So typically, for Gaussian processes, we think of our index being the real line, or Rn, some Euclidean space. And then we think of this as a function. But a stochastic process is just a collection of random variables. So if our index set is infinite dimensional, we get an infinite dimensional process. There's an infinite number of random variables in this stochastic process. But thankfully, we know that to fully specify any stochastic process, for any finite dimension, any infinite dimensional stochastic process, all we need to specify are what are called the finite dimensional distributions. So the finite dimensional distributions are, consider any finite set of indices. So I've got x1 to xn, so just n different indices, so n different points in space. Then all you need to be able to specify is the joint distribution of those n random variables. And if you can do this for any n and for any set of indices, they're what are called the finite dimensional distributions. And if you can specify all of them, mathematicians can prove that you specified uniquely, or at least almost surely, the stochastic process. So what is a Gaussian process? Well, a Gaussian process is a stochastic process which has Gaussian finite dimensional distributions. So in other words, it's a collection of random variables such that if we look at the joint distribution of any finite number of them, that has a multivariate Gaussian distribution. That's it. That's the entire kind of story, if you like. So it's got a multivariate Gaussian distribution. I've got slightly different notations, Neil, with some mean vector. So this is a column vector of n numbers, and a covariance matrix, which will be an n by n matrix, a positive definite variance matrix. And kind of all the modelling effort of Gaussian processes goes into how to choose, the mean and the covariance, which is what we'll talk about. Okay, so this sounds like quite a restricted class. You've got all the, a choice of many different stochastic processes. Why choose Gaussian processes? Why kind of limit ourselves to this particular class? So I've got various answers. I think I've got 3 or 4 different answers for why Gaussian processes are a good choice. And then I'll talk a bit at the end about the problems of using Gaussian processes a little. Okay. So Neil talked about this a bit, but I think it's worth repeating, and I'll go through a bit more detail. The main reason we use Gaussian processes is that Gaussian distributions have are very mathematically flexible and a nice family to work with. So in particular, if we've got some vector x that has a Gaussian distribution, multivariate Gaussian distribution with mean, mu, variance, sigma, then x is Gaussian if and only if all the linear combinations of x are Gaussian. So we take any matrix A, that you can multiply x by, then if x is Gaussian, ax is Gaussian. And all we have to do is transform the mean in the same way. So ax has mean a mu, and the variance transforms similarly. So what does this mean? Well, it means that sums of Gaussians are Gaussian. If a is a row vector of 1s, a times x is just the sum of all the terms in x. And so we're saying if x is Gaussian, the sum of all the terms in x is Gaussian. That's nice. The marginal distribution is x. So the marginal distribution of x is Gaussian. Okay, so if a was 1, 0, 0, 0, 0, 0, okay, a times x just picks out the first element of x, and it says that is Gaussian. Okay? So there's a nice property to have that is not true for many other distributions. Okay. But the main reason we use Gaussian processes are that they're still Gaussian when we condition upon them. Okay? So let's imagine we've got two random variables, okay? An x1 and x2. Okay? And this has got mean, which I'm going to write as mu1, mu2, okay? And a variance matrix. Okay? Okay. So we've got a random variable, and you can think of these, each of these could be vectors if you like. Okay, this just split up a vector into two parts. But let's just imagine we've got two random variables from it. Okay? Oh, I've written on the bottom. The nice thing about Gaussian distributions is that if we observe x1, okay, then x2 is still Gaussian. Okay? So let's suppose we've got a multivariate distribution, we observe one component of it, okay, or some random variables, then our belief, so our distribution for x2 is still Gaussian. Okay? And all we have to do is slightly modify the original things. Okay? So the marginal for x2 originally is that it's normal mu2 sigma 2, okay? But if we look at the distribution of x2 once we observe x1, well, x1 should tell us something about x2. Okay? So what we do, we just modify the mean a bit. Okay? So mu2 becomes mu2 plus a bit, okay? And the bit we plus is how surprising x1 was. So it's x1 minus its mean, that's how far it was from our prior expectation, scaled by its prior variance, and then scaled by how related it is to x2. Yeah? So that's kind of a natural, plausible, natural-looking formula. Okay? The variance we think we have for x2 is just the prior variance for x2 minus a bit where we've got something about the information we got in x1 and how related they are. Okay. So I think it's useful just to see where this comes from once, yeah? If you've not seen this before. So we'll just very quickly work through the detail. I was going to do this on board, but I've added the algebra by hand while Neil was talking, and now there's a whiteboard, but it wouldn't have fit anyway, so that's okay. Okay. So we want the distribution of x2 given x1. Okay. So that's the distribution of x1 and x2 divided by the distribution of x1. Okay. Or in other words, we only care about the x2s here. Okay, so that's just proportional to the distribution of x1 and x2. Okay, so let's work that out. Okay. This is the multivariate normal form that Neil gave before. Okay. So if I just expand this out with the matrices and vectors, okay, we've got this is the vector x1, x2 minus the mean mu1, mu2 transposed times the inverse of the variance matrix, which I'm going to call Q, okay, and I'm going to block it up in the same way, okay, times this term again. Yep. But all we care about here are the x2s, right? Because we want to know the distribution of x2. Yep. So let's just expand this out, and we'll just keep hold of the terms that have x2 in. Okay. So we get an x2 minus mu2 times a q22, x2 minus mu2, and then we get the cross terms. So we get x2 mu2, q21, x1 minus mu1, etc. Okay? And then we get some stuff left over that doesn't have x2 in. Okay? So what we got here? Well, we've got a quadratic term in x2 and a linear term, so quadratic in x2. So what distribution is this? Well, it's just Gaussian. Yeah, that's what a Gaussian looks like. It's e to the minus a quadratic in your variable. Yeah? So all we have to do now is just collect the terms to work out the mean and variance. Okay. So if we just look at these bits, okay, so that's the same as we had on the previous slide, okay. So if we just keep our eye on this bit over here for a minute, this is going to give us the mean bit, okay. So I'm just going to write it out slightly differently. So I've just collected the squared terms in x2. So I've got an x2, q22, x2, okay. Then I've got the terms that have x2 in once. So that's an x2 times q22 mu2. That's this bit, and an x2 q21 x1 minus mu1. This bit here, okay. So if we just complete the square, we get the the posterior mean, if you like. Okay. So what this tells us, so all I've done here is this is x. I've just completed the square here. I've got a squared term, a linear term, plus some junk. Okay. And I've just collected this, so it's x2 minus this bit in here. Okay. Scaled by the inverse of this thing. Okay. And so we get our posterior. Okay. So it's very simple. 3 or 4 lines of linear algebra gives us the posterior distribution of x2, or the conditional distribution of x2, when we observe x1. Okay? It's just a modification to the prior mean plus a variance. Okay? I think you just need a bit of matrix algebra to make these terms back in the original terms we had. So you can write Q22 inverse in terms of the original sigma, okay, and so on. Okay. So I always like saying these things. Right? I did a maths background, so I think it's useful just to work through these calculations just once. Okay. So, why is this useful? Okay. So let's now switch from distributions to Gaussian processes. Okay. So that was just for Gaussian distributions, so just a fixed set of endpoints. Let's imagine now we've got Gaussian processes. Okay. So I've got a Gaussian process, okay, and I'm considering it at x1 to xn, okay, and then an additional point, f of x. Okay. So what I'm going to imagine is, well, these are just n plus 1 index points. Okay. So we know that it's a Gaussian process, it must have a Gaussian distribution at these n plus 1 points. Okay. And we're going to imagine what the distribution becomes when we observe f of x1 to f of xn. What do we get left as the distribution of f of x? Okay. So if this is the prior mean, prior variance, okay, when we observe the function value at x1 to xn, so this is the distribution of f of x given f of x1, f of x2, f of xn, we get it still Gaussian, okay, but with just a modified mean and variance. Okay, so the modification is just this modification. Yeah, a split up mu1 and sigma 1. Okay. So that's all it is. All Gaussian processes are. Okay, to work out the distribution for any new value of the function, the value of the function at any new value of x. Okay, we just start off by thinking about the joint distribution with the observed data, and we just condition. Yeah. Okay, so this is typically what we think of. If I have my index values being all the points along here, okay, let's say I put 1,000 points between 0 and 10. Okay, so I've got f of x1, which is f of 0, f of x2, which is f of 0.001 or something. Okay, and to begin with, we just have this being specified as a multivariate Gaussian distribution, and if I simulate from this multivariate Gaussian distribution, I get curves. Okay. Let's say then we're told f of the value of f at a small number of locations, okay, for these 5 locations here. Okay. Then we can work out the posterior distribution of f at all these other locations, okay, and we get it still a Gaussian process. Okay. So these are some random samples from the process conditional on the Gaussian process going for these points. Okay. Or you could draw it this way, where I've got the mean and the variance, the uncertainty about it, so standard deviation. So you're going to create some of these plots this afternoon. Okay? This is the basic idea. You start with a prior specification of what your functions look like, you condition them on data, you get a posterior specification of what your function looks like. Okay? And for these plots, the way we think about this is we just do predictions at all these locations along here to get a mean and a variance. Okay? And it gives us pretty pictures like this. Okay? Okay, so why use Gaussian processes? That's what they are. Why use them? Okay. So the first answer we've already hinted at, it's just because they're closed under all these different types of operations. Yeah? There's various classes of models we could use. Yeah? I could use neural networks. I could use T processors. I could use, there aren't that many named processors, but there are lots of choices you could imagine using. Okay? The nice thing about Gaussian processes is that we can do lots of stuff to them, and they still remain Gaussian processes. Okay, so I take 2 Gaussian processes, I add them up. It's still a Gaussian process. Okay. More importantly, they're closed under Bayesian conditioning, which is what we've just been working through. Okay, so if I observe the value, the function, a bunch of values, okay, then my conditional belief about the function given the observations is still a Gaussian process. Yeah, and that's the key point, really. Yeah? under Bayesian conditioning, they are still Gaussian processes. And all we have to do is change what's called the mean and covariance functions, which we've not properly introduced yet, but it's just kind of changed something you keep track of in terms of how you calculate the mean and the covariance of these things. Okay? But it's still just a Gaussian process. Okay. It's also, interestingly, closed under any linear operation. Okay. So if f is a Gaussian process, okay, and L is some sort of linear operator, so obviously this is a linear map, adding things, okay, but we could have other linear operators, like differentiation is a linear operator, okay, integration is a linear operation, okay. I could take the divergence of a vector field, okay, so on, okay. Any linear operator is still a Gaussian process. Okay, so any linear operator applied to f, we just get a different Gaussian process, but we just apply the linear operator to the mean function and to the covariance function twice, basically. Okay, we can talk about the details if you want. Okay. But this is really nice because this allows us to build structure into things. You could have observations not only on the function, okay, so I could observe the function, but I could observe its derivative. Okay, I could observe its integral. Okay. I might know it's an incompressible field, so it has zero divergence, yeah? Or a conservative field, so it has zero curl. I can build those things in as well, yeah? Because they're just linear operators. Okay, so I'm going to tell you a little bit about how we determine the mean and covariance. Okay? So we think of these things just as functions, okay? And the honest answer is we just do it by trial and error, essentially. We have kind of choices we like, okay? And we're limited in the choices we can make, okay? And we try things out and see which ones work well, okay? And you build up intuition, and but there's not much theory about how to pick, optimal choices for the covariance function, for example. It's kind of, we try things and see does it work, okay? But there are some rules about how we can pick them, and we have to make sure we satisfy. So we can think of the mean function, whoops, we typically call it m of x, okay, so it's just the expected value of the function at x, okay, and there's no rules here, you can do whatever you like, okay, you can pick any mean function you want, you're kind of limited only by your imagination, okay, and so in machine learning they tend to pick 0, yeah, we argue with Neil about this all the time, he's not even here, unfortunately, okay, whereas in statistics, we tend to have less data and we care a bit more about interpretability, okay? And we tend to pick kind of some sort of parametric mean function here, okay? And this is also limiting, right? By the time you've imposed something, a particular structure for your mean function, you've limited your possible set of functions in some way, okay? But you could pick whatever you like here, essentially. Okay? 0 works great if you have a lot of data. And you're not extrapolating beyond your data. Okay? If you want to extrapolate, then kind of the parametric structure, it still tends to work well. Okay, this is slightly technical, okay, but one thing we often do is you might have your mean function being some unknown parameter times a known mean function, okay? So you could have a particular basis. So this just could just be straight lines, it could be quadratic terms, it could be sinusoidal terms, whatever you like, okay? And the nice thing is, as long as we give beta a Gaussian prior, okay, that includes the improper flat prior, one everywhere, okay, then where we can integrate out the dependence upon beta, okay, so f, the distribution for your function given your the data and the parameter is still a Gaussian process, of course, but you can integrate out the unknown parameter beta and you still get a Gaussian process. Okay, so the kind of the normal rules of linear models still apply. Okay? You just have slightly modified variance formulas. Okay, we can also use, but the most important thing about Gaussian processes is not really the mean function, it's the covariance function. Okay, they're the interesting part of GP, if you like, and where all the work gets done, as Neil was saying earlier. And so the general specification, of course, for Gaussian process is just a Gaussian process is just one where a finite collection of random variables is a Gaussian distribution. Okay? But how do we determine the mean and variance? Well, the way we tend to determine the variance is by simplifying things and using a covariance function. Okay? So we say that the covariance between f of x and f of x prime, okay, is k of x and x prime. Okay, so it's a function of the locations. Okay, and there's some rules about k, which Nicola will talk about later, I think. Okay, but the main one being it's got to be positive semi-definite. So in other words, when we look at the matrices that are formed by applying k to all the different indices, it's a variance matrix. It's a positive definite matrix. Okay. And as I say, this is really where the trouble starts with Gaussian processes, in a sense. Okay. One, because we get lots of numerical instabilities, but this requirement to be positive semi-definite really limits what we can choose here. Okay. I mean, there are an infinite number of choices, but the ones we know about and can write down nicely and simply limits us to a handful of choices, really. I mean, not quite a handful, but in practice, people tend to start with building blocks of 4 or 5 different choices and combine them to get more interesting choices. Okay. Okay, and again, just a technical point. Okay, if our covariance function has an unknown parameter, the scaling the thing. So, say if we wrote the covariance in terms of a correlation function and an unknown parameter, sigma squared. Okay, we can again give sigma squared a prior distribution. Okay, so as long as we give it an inverse gamma prior, okay, and that includes the improper prior 1 over sigma squared. Okay, then we can again integrate out the dependence upon sigma squared to get another process. Okay, but now we don't get a Gaussian process, we get a T process. Okay, which has slightly heavier tails. Okay, but the degrees of freedom of this thing is the number of data points minus the number of parameters in your mean function. Okay, so in practice this is large, and so in practice this looks like a Gaussian process. So again, in practice we can integrate this thing out and get something that's still pretty much a Gaussian process. Okay.
And this scaling is squared just to keep it positive?
It's scaling squared just because of convention we tend to write variances as parameters squared. Okay, so yeah, ignore the square. It's just the name is sigma squared. Okay, it's how I think of it. Yeah, how statisticians tend to think of it. Yeah.
You showed how you could parameterize the mean function in terms of a hyperparameter, which itself was Gaussian.
Yep.
The covariance function, is it possible to use a distribution over positive semi-definite matrices as well? Or is it generally a deterministic function of the
If I've understood so generally it's a deterministic function. Okay, you may have parameters in there that you don't know. Okay, and we can learn those parameters. Okay, but for most choices of covariance functions, the analysis is not conjugate. Okay, which means that we have to do either sort of like maximum likelihood to estimate them or MCMC to integrate them out.
For example, I think it's a Wishart distribution which you can use to draw random covariance matrices.
Oh, I see what you mean. So just a random distribution from the matrix. Yeah. Okay, so I think the question was, could we use something like a Wishart distribution to generate random covariance matrices? Is that?
Yes.
Yep. I think the problem with that was how do you make sure it is consistent when you have differing inputs? You know, if you're just worried about the same n inputs all the time, that might be something sensible. But if you could take any set of n inputs from an infinite number of possibilities, how do you get Wishart distributions that make sense? That's not to say it's probably been done, right? Does anyone know? No. Okay. Yeah, that'll be my guess about the problem. Okay. So let's just look at some examples. So Neil showed us some examples. Okay. So the covariance functions, you kind of you want to think for a given covariance function. Let's do some examples, and I'll say the comments in a minute. Okay. So this is a particular choice of covariance function, often called a radial basis function, okay, or squared exponential, or exponentiated quadratic, or sometimes by misinformed people, a Gaussian covariance function. Okay. It just takes the difference between x and x prime, squares it, okay, and does e to the power of it. Okay. And so if we generate random samples from this, we get these very smooth functions. Okay. So let's change it a bit. We'll look at something. Okay. So all I've done now, I've took the same covariance function, but I've divided by a scaled x by 0.25. Okay. And now we get the same kind of smooth functions, but they vary much quicker. Okay. Because I've changed my length scale. Here, my 1 is kind of the relevant scale for these things. Now the relevant scale is 0.25, and so what was varying over things of length 1 before, okay, now varies 4 times as fast, and so we've got functions that go up and down faster. Okay? Look at one more. If I divide by 4, I've kind of stretched space. Okay? So instead of 1 being the relevant scale, now 4 is the relevant scale, so things vary much slower. Okay. So this number here, we tend to call the length scale, okay? And this is what, Nicola will talk about this in much more detail. This is a hyperparameter that we need to estimate. We need to learn the relevant length scale for our problem, okay? So let's look at a different covariance function, okay? I've scaled it a different way. So now I've still got 1 as my relevant length scale. I've just scaled by 100 at the front here, okay? So all that has done is made the variance of the process bigger. So here, it varied between 3 and -3, like a good Gaussian should, 99% of the time. Now I've scaled it by 100, so it'll vary between square root of that times 3. Okay, so 30 plus or minus 30. Yep. So that's all that number's done at the front. It's just changed how variable it is. Okay, so that's one particular family of covariance functions called exponentiated quadratic. Okay. Or RBF, I think, in GPy. Is that, yeah? Okay. There's a different family. This is the Matern family. And there are various choices of Matern, but this is the Matern 3 over 2. Okay, so here we've got the absolute value of x minus x prime, okay, times something at the front. Okay, and so you can see now we've got functions that are much less smooth in some sense. Okay. So you can stare at these covariance functions for a long time to think, why does this give functions like this, okay? And why does this give smoother functions? And I don't think there's any answer to that question, basically. There's kind of mathematical rules that help, help us determine the properties that are going to result from the functions, but I kind of get nothing by staring at the functional form and thinking what's going to happen here. Maybe some people do. Okay. So the properties we can intuit mathematically are things like, for RBF functions, covariance functions, we're going to get sample paths that are infinitely differentiable, they're analytic functions. Okay, so they're very smooth, they have derivatives of all order. Yep. Whereas from the Matern 3 over 2, we get functions that are only one time differentiable. Yep. So these functions, you could differentiate them once, and then they become non-differentiable. Okay. You can have Matern 5 over 2, and Nicola will talk about these things a bit more, I think, and that'll be twice differentiable. Okay. Yeah, 7 over 2, 3 times differentiable, and by the time you got to 7 over 2 and 9 over 2, they're practically indistinguishable by the eye from RBFs. Yeah?
Where does this 3 over 2 come from?
I think there's a whole family of Matern covariance functions indexed by some parameter here, okay? But for powers of half, so 3 over 2, 5 over 2, 7 over 2, they have a nice form that we can write down without, is it Bessel functions? Yeah. They become nicer expressions. So there is a whole family of Matern covariance functions. Okay? It's just these are the ones I can write down nicely and compute nicely. Otherwise, we need Bessel functions.
But squared exponential functions also look non-smooth if you reduce the length scale.
Yeah, but they'll still be differentiable. They'll still be infinitely differentiable, even if they wiggle around a lot. Okay? They vary fast. Okay? They're still infinitely differentiable. So one of the odd things about this, if you told me the value of this function here and told me all the derivatives of this function at 1, okay, you could reconstruct the entire function. Right? That's a property of analytic functions. So they're not necessarily good choices, but they're widely used, the most commonly used covariance function, I'd say. Okay, another covariance function, Brownian motion, is a Gaussian process, of course. Okay, so Brownian motion always starts at 0. Okay, and the covariance is just a minimum of x and x prime. I have no idea. Again, from this, how you would gather it with something like this. Okay, so this is a nowhere differentiable function, and it's infinitely variable. So in any finite, arbitrarily small interval, you could find the complete works of Shakespeare written in your own handwriting if you look close enough. Yeah, it's infinite variation. Yeah, so they wiggle around a lot. Yeah. If you differentiate Brownian motion, okay, you get white noise, so that's just uncorrelated things. Okay, so this is the white noise covariance function. So it's 1 if x is equal to x prime, and it's 0 otherwise. And that is just, for each number, it's just an independent random variable. Okay, so it's just a white noise process. Yeah. If you integrate this, you get Brownian motion. Okay, so our Gaussian process inherits all its properties from the covariance function. Yeah? And there's mathematical rules for figuring these things out. The main thing is like differentiability. You can tell how differentiable your Gaussian process will be by the number of derivatives the covariance function has at 0 if it's a stationary process, and so on. Okay? You get the smoothness, or how quickly it varies from its length scale, and its variance from the number out front, and so on. Okay? And these are all things we might want to estimate when we fit models to data. Okay, so just one final example to motivate the next thing. If I use the covariance function x times x prime, okay, so the transpose of it is higher dimensions, okay, and draw random samples from this, okay, what I get are straight lines through the origin. Okay. So why is that happening? Well, if we imagine we've got a function f of x, which is just a straight line for the origin, c times x, okay? And let's suppose we give c a normal 0-1 distribution. Okay? Then if we look at the covariance between f of x and f of x prime, this is the covariance between cx and cx prime. Okay? X is not random, okay? So x transpose, variance of c, x prime, so we get x transposed x prime. Yeah? So, functions of this form have this covariance function. Okay? So, straight lines for the origin have this function. I don't know how to do the reverse proof, actually, to show that random samples from the Gaussian process that have this covariance are straight lines, but Nicola can probably do it. But anyway, certainly, straight lines have this covariance function. Okay. So, what we're going to do now is talk about how we can generalize this, how this generalizes to give more complex covariance functions.
How does that work for the left-hand side of 0?
They just go back the other side.
Okay.
Yeah.
Multiply, you pick two x's, one which is negative and one which is positive.
Yeah, that'll be okay.
Multiply, you're going to get a negative
That's okay.
entry in your covariance, won't you?
That's okay.
Yeah, okay, that's
Yeah.
fine.
Yep. As long as the diagonals are positive, which they would be. Yeah. Are there any other questions? Yeah.
You mix the types of Gaussian
Absolutely.
functions, including length scales, for example.
Yeah, absolutely. So Nicola will talk about this in much more detail later, but there are a few other kind of core types of covariance function that we can write down. Okay? But generally, then how we get more complex models are by adding them, multiplying them, and doing all kinds of weird and wonderful things with them. Okay? Well, generally adding them and multiplying them, actually. People then look at deep Gaussian processes, which are no longer Gaussian processes, where they nest them and so on. But for just plain Gaussian processes, people tend to start with these building blocks and combine them. Okay? So you might have two RBF covariances added of different length scales. Okay? One to get a kind of slowly varying thing, and one to get a fast varying aspect, for example.
Is there an analytical way to do that?
You mean to learn the covariance function? You can always write down the log likelihood of the fitted model, okay, and use that to search the space of different models. Okay. In practice, I don't know how much that is done. I don't know if anyone knows, but yeah, you can certainly use all the normal tools of statistics to search, the possible different space for covariance functions. Yeah. Okay. Yeah.
Do you estimate such a covariance function from data as well? I mean, in CL Gaussian, you can estimate autocorrelation function. So you apply the same reasoning, apply your covariance.
So for estimating the covariance at places where you have data, sure. Okay. What becomes difficult is for the Gaussian process, you want to estimate the covariance of the function everywhere. Okay. So estimating the covariance at points where you don't have data, you then need some way to get from your estimated covariance to somewhere else. And to do that properly, you need a positive definite function. It needs got to be positive definite, and that reduces us back to this kind of world, I think.
Yeah.
Yeah?
Does this selection of covariance function just give you linear regression?
Yeah.
Is that what we're saying?
Yeah, that's where we're headed. Yep. Yep. Let me just, got no concept what the time is. Okay. Any other questions? Okay. So that was the first answer why we should use Gaussian processes. They're a flexible family. The second answer is that they generalize linear regression in some sense. Okay? They give us a non-parametric or kind of kernel regression. Okay? So what we're going to show, or what we're going to kind of say, rather than show, is that K determines the space of functions that the Gaussian processes model lives in. Okay? So with this covariance function, we know that our fitted model is going to be straight lines through the origin. Yeah? For other covariance functions, we get different spaces. So Gaussian, Brown in motion is scaled step functions added up. Okay? And so on. Okay, so let's start with linear regression. Okay, and then we'll generalize the linear regression fit to other more exciting kernels. Okay. So linear regression, let's suppose we're given xy pairs. Yeah? And our model, maybe x is multiple dimensional. Yeah? Our model is that y is x transpose beta plus epsilon. So just linear regression, a linear model. Okay. How do we typically do linear regression? Well, we minimize the sum of squared errors. Yeah? So we look at the difference between y and x times beta. So I've written x as the design matrix here. So it's all the lowercase x's stacked, one row for each. Okay, so x1 in the first row, x2 in the second row, etc. Okay. And we minimize the data, the model misfit. Yeah. And we might regularize in some way so we don't overfit. So this is ridge regression, right, or Tikhonov regularization. Yep. So we're going to find the beta that minimizes this, the sum of squares error plus a penalty term to stop us having too interesting a choice of beta. Okay. So everyone saw this, I imagine, as an undergraduate. If we do this, we get the estimator, which is x transpose x plus sigma squared I inverse x transpose y. Yep. Standard formula. We can rewrite this, though, as in what's called the dual form. Okay. So this is the bit I added in because I couldn't do it on the board. Okay. So just look at these two lines for a minute. Okay. We've got, hopefully you can see these two expressions are the same. I've just taken x transposed out either on the left or the right of this expression. Okay. And if I then multiply, left multiply by the inverse of this, I get this on this side. Right multiply by the inverse of this, I get this expression. Okay. And so if I swap this bit, okay, for this, I get the dual form here. Okay. So why is that useful? Okay. So this was the form you know from when you were an undergrad. Okay. This is the dual form. Okay. But this makes it look like we made the problem harder. Okay. The standard way of writing linear regression, we've got x transpose x, which is a p by p matrix, where p is the number of parameters. Yeah? And we've got to invert that p by p matrix. Okay. Here, we've got x transposed, okay, which is an n by n matrix, and which is the number of data points. And typically, you're going to have more data points than parameters. Okay, so this is, you have to invert a p by p matrix, order p cubed. This is invert an n by n matrix, order n cubed. So this is more work in most cases. So what's the advantage of doing this dual form? Okay. Well, the advantage is the dual form only uses inner products. Okay. So if we look at what x transposed is, x was just the individual observations in rows, okay, times by x transpose, which is the individual observations in columns. Okay. If we look at this, we get what's called the kernel matrix, okay, and it's just inner products. Okay. So I get x1 transpose x1, x1 transposed x2, x1 transposed xn, okay, and so on down to x n transposed xn. Okay. So you're still probably utterly confused why this is useful at this point. Okay. But what we could do is replace this inner product by something more interesting. Okay. This is what's known as the kernel trick. Okay. So let's see how it works first. So let's consider making a prediction of y at some new location x prime. Okay. So our prediction under linear regression is just going to be x prime times our parameter beta hat. Okay. So if I write in my estimate of beta hat in the dual form, okay, what we get is this is just an expression that only uses inner products. Okay, so k is what we had before. Sorry, this that was this thing. Okay, that's what I'm calling k. Sorry. And then at the front here, we get x prime transposed times capital X transposed, okay, and that's just the vector that has x prime x1 in a product, x prime x2 in a product, and so on. Okay, so you need to sit and stare at this for a bit, but it's only using inner products between our input locations all the time, inner products only. Okay. So, as someone said, a question a minute ago, what we've retrieved here is just linear regression at this point, okay? But it looks exactly the same as the Gaussian process thing we got before, okay? So, if we're doing Gaussian process regression, but the particular kernel I used, covariance function I used, was x transposed x prime, that is exactly this. Yep, that's exactly what we got to. Okay? But what we're going to do, instead of using this linear covariance function, which gives us straight lines, we're going to replace this by something more interesting. Okay? So when you did linear regression, you probably all know that you can replace x by a feature vector. Okay, so we could have it 1x and x squared, okay, and that would give us quadratic fits. Okay? Or if I add an x cubed in here, I get cubic fits. Yeah? The clever thing about these kernel methods is we're going to have an infinitely long vector of features here, okay, to get an infinitely rich family of models. Okay? And what's even cleverer is we're never going to have to think about what these features are. Okay? Okay. So for some particular choices of feature vectors, okay, so things like this, okay, the expression for the inner product between them becomes very simple to compute. It's just a simple kernel function, okay, that's easy to compute. So let's just see an example. Okay. So let's suppose my feature vector was just Gaussian humps. Okay. So let's suppose I split up the region I'm interested in into n bits, and around each one I just put a Gaussian curve. Okay. Then my feature vector, if I just looked at the functions, the feature for a new point x was just x minus the location C1 scaled somehow, okay, and I collect all these things for all my different n features, okay, and create this vector. Okay. Then, if we let the number of features grow and grow and grow, okay, and there's no detail here, the inner product between any two feature vectors becomes this RBF kernel. Okay, so the math is not here, yeah, I'm not showing you anything, but if I was to keep infilling more and more features, more and more Gaussian curves in slightly different locations, all the same shape, just shifted slightly along, okay, then once I did that to fill in everywhere, okay, and got the infinite feature vector, when I did the inner product, I would just get the RBF kernel. Okay. So let's just see what that looks like here. Okay. So let me just make this plot a bit bigger. So I'm going to start with 4 features. Okay. Can you see that at the back? Is that too? Yeah? Okay. So I've got 1, 2, 3, 4, 5, 6, 7 data points. Okay. I've got 4 feature vectors, which are these 4 curves. Okay. And so I'm going to do linear regression, just plain linear regression, okay, with 4 numbers. Okay. So for each point in x, I work out what the value of this function is here. Okay. For this function here, and so on. Okay. So if I it's made my text really small. If I evaluated, you can't read that at all, but okay, if I evaluated my feature vector at a particular location, I get 4 numbers for these things. Okay. And all we're doing then is just linear regression using these 4 numbers. Okay. And I get my linear model fit here. Yeah. So it doesn't look very good. But as I make the number of features get larger, so if I do 40 features, I'm going to start to get a curve that goes through all the data points. Okay? And in the limit, if I took a large number of points here, okay, let's just do 400, otherwise it'll take too long. We converge on what the Gaussian process fit would be with the RBF kernel. Okay? Yeah, it does. Yeah. Gaussian process. This is guaranteed to be smooth. I'm just crap at computing. So, yeah. So, the point I'm trying to make is that what we're doing with Gaussian processes is we've greatly expanded the power of linear regression. Okay? Linear regression, we're kind of limited to our imagination about these set of features. Okay? With Gaussian processes, we don't choose these features, we choose the covariance function. Okay? But any covariance function corresponds to an infinite, well, a set of features, possibly infinite set of features, okay, that we never need to think about. Okay? But by having that infinite set of features, we get a very rich family. Okay. Okay, so this is known as the kernel trick, right, in machine learning. Okay, so it's normally presented for support vector machines or classification kind of problems. Okay, you've probably seen this picture before, right? You're trying to separate these two data sets. You can't do it with a linear kernel, but you can by projecting into some higher dimensional space. Okay, these kernel methods mean we don't need to think about that higher dimensional space. We just choose a kernel and try it by trial and error, basically. Okay. Okay, so I've said this, we don't choose a kernel, we don't choose the features, we choose a kernel, okay? That's just a positive definite function. Yep. And any kernel implicitly kind of defines a set of features, okay? Probably an infinite dimensional set of features, okay? But we don't think about these. Yeah? It just is a set of features. For the RBF kernel, okay, we get Gaussian features. I mean, this feature vector is not unique. There are different ways of writing it down, yeah? But we get a set of features. And our model, then, of the space of functions we're considering are linear combinations of this set of features. Okay? So when we do RBF, Gaussian process of RBF, we're assuming that our function is a linear combination of Gaussian humps like this. That's essentially what we're doing. Okay. And this is the point, okay? Although reality might not really lie in this space of functions, this is called the RKHS, reproducing kernel Hilbert space. Okay? Although, so we're working in a larger space of functions, okay? And although reality might not lie in that space of functions, it's a very rich family of functions. Yeah? And if you choose it rich enough, it may be dense in a set of continuous smooth functions. Yeah? So this is the idea behind non-parametric methods, right? We don't want to limit ourselves to linear regression or our imagination, so we work in this infinite dimensional space, okay, which brings problems, but it gives us this very rich family to work within. Okay. Okay. Yes?
Among that space of functions that are generated by the RBF kernel, is x squared living in there somewhere? Is the family of x squared in there?
Probably not. I can't answer that question, but Nicholas, no. So constants are not in there. Straight lines are not in there. Yeah. So no, basically. Yeah. So this is the space of functions. It's if these are those Gaussian humps. Okay, you've just got all finite linear combinations and the completion of those set of infinite combinations of these things. Okay. So no, I can't prove it, but x squared probably isn't in there. Okay. Any other questions?
Why don't we just limit ourselves to doing kernel-based regression and stop there?
Instead of linear regression, or instead of
instead of doing Gaussian process modeling, why don't we just say, well, we'll take linear regression as a model,
yeah,
and introduce kernel functions to get beyond linearity and just stop there.
Well, you wouldn't have a probabilistic interpretation then, okay? Oh, the question was why not limit ourselves to kernel regression? Why, I guess, add this stochastic interpretation on top? Yeah, because kernel regression, there's nothing statistical there. It's essentially the same theory as splines. Yeah? So I guess Gaussian processes, if you want to live in a stochastic modeling framework, a probabilistic modeling framework, so it gives us ways of making probability statements as well. Yeah. So, yeah. Okay. So I think I've got two more answers why I use GPs. Okay. So one answer might come from this field called Bayes linear statistics. So has anyone heard of Bayes linear methods? Are you from Durham by any chance? Nothing, okay. So there's this fantastic body of work that comes from Di Finetti's original kind of idea. So Di Finetti is like the founding father of subjectivist statistical methods. And it was taken up by Michael Goldstein in Durham, who's been working on it all his career. He's retired now. Okay? And there's a body of people who kind of worked with Michael essentially, and a few others who found it by themselves. But the idea is, how would we do statistics without probability? Yeah? The problem with using probability for a Bayesian is to write down a prior distribution for some quantity. Well, a distribution is an infinite number of judgments. Yeah? It's a countably infinite number of judgments whenever you write down a distribution. And a true subjectivist might think that's impossible to make that many judgments. Okay? So the question is, how can we do it with a finite number of judgments? So how do we do statistics if we only knew the expected value of our random variables and the variance of them? Okay, so that's, say, 2 quantities for each variable. And we might imagine, as a subjectivist, someone who believes you should do subjective methods, okay, that you could elicit those quantities from someone. Okay? So if we had an x and y, how should we do statistics? Okay. So there's been a variety of proofs about the right thing to do, okay, and they all lead to the same answer. Okay. But if we wanted to say, what do we expect about x given our observation of y, okay, then you can argue by coherency or geometric arguments or various other arguments. Okay? But the only right thing to do is to say, well, the expected value of x given y is the expected value of x plus the covariance between x and y plus the inverse of the variance of y times y minus the difference from its expected value, okay? Which is exactly the Gaussian process update. Okay? So if you wanted to do statistics only using the first 2 moments, mean and variance, the formulas you'd use to do Bayesian type things to update your beliefs would be exactly the Gaussian process thing. It's not a surprise, right? It's a very natural point of view. Okay, so GPs are in some sense kind of second order optimal. If you only got the first 2 orders, first 2 moments, they're the right thing to do. These things have been rediscovered multiple times. Okay, so kernel Bayes is a really exciting kind of area, which I know Neil's fond of, developed by Arthur Gretton and many colleagues, okay, which basically takes this kind of idea and does a kernelized version of it. Okay. So instead of using just the first 2 moments, you've got an infinite number of moments, but it's got exactly the same formulas come out of it again. Okay. So that's popular machine learning. And much older is kriging. Okay? So kriging, again, has no distributions in it. It's just what is the best linear unbiased predictor you can come up with. Okay? And it's the same formula. Okay? So there's nothing about Gaussians there at all. It's just this is the best thing to do if you want a best linear unbiased predictor. Okay? So it's a very natural kind of framework to work in some sense. Okay. I guess the final thing is we get these uncertainty estimates from emulators. Okay, so your question was, why not just do kernel regression? Well, many of us like to do probabilistic modeling, basically. Okay, so Gaussian processes give us an estimate of probabilities.
Is there other methods as well to achieve that?
Yes, I'm sure. Like what? Many, yeah, I'm sure. Yeah. Okay. So the GPs come equipped with the uncertainty in their prediction. Okay, and that's kind of widely used. Okay, so not only are you predicting the value in places you don't have data for, you're predicting it with uncertainty. But it is Gaussian. Okay, so that is the limitation. Okay, so just one warning then, which you'll see undoubtedly this week in the lab sessions in the afternoons. Okay, the uncertainty estimates from a GP are very often flawed. Okay, so if we've got data x and y, okay, inputs and outputs, okay, our variance about the value of the function at some new input x given this data, okay, is this formula here, okay, and it doesn't matter what the details are, but the key thing is that y doesn't appear here at all, okay. So your variance, your estimate of the variance at some new location doesn't depend anywhere on the y values you've seen. It just depends on the x values, other than the fact that you probably estimated some hyperparameters which you will have used the y values for, but it doesn't directly depend upon y, and I think that's a kind of a real flaw in the model quite often. Okay. The other problem is that the variance estimates are particularly sensitive to the hyperparameter estimates. Okay? The mean, not so much. The mean tends to be relatively robust, but the variance can be much worse. Okay. Okay, so I thought I'd just then talk about a few difficulties of using Gaussian processes, just to kind of finish, which you'll definitely discover for yourselves this week. Okay? So all this theory is fine if you know what covariance function you should use. Okay? GPs are great. Okay? The problem is we don't know the covariance function. Okay? We might not know the right length scale, the right hyperparameters, so on. Okay? And we have to estimate them from data. And that's really where Gaussian processes start to get messy and hard work, to be honest. Okay? So typically, I've already said this, we tend to pick covariance functions from a small set, usually based on things like differentiability. So I might want a very smooth thing, so I might have an RBF thing, or not too smooth, so I might have a Matern 3/2, or something like this. Yeah. And then we might try a few combinations of covariance functions, adding them, multiplying them, etc. Okay, and might evaluate their fit to the data using, say, the log likelihood. Yeah, see which one fits best, or I might do some predictive tests. So I might leave some data out and predict that left out data, okay, and use that to pick the covariance function that works best. Or I might do some kind of cross-validation. Yeah, there's all the usual tricks to try and find the right family of functions to work with. Okay. So yeah, there's these hyperparameters that we also need to estimate. So for the RBF, we've got two hyperparameters. Okay, the length scale, which is the thing that divides x, okay, to tell us how fast the process varies, and a variance. Okay, and although we can integrate this out in theory, in practice we tend not to. Okay, and this we can't integrate out for any conjugate prior, and so we have to either just estimate it and fix it, or use like maximum likelihood, or MCMC, some sort of Bayesian inference. But it's computationally expensive. Okay. Okay, so I think there's been increasing realization that GPs are rather complicated structures. Okay? And whenever you use a Gaussian process model, you're imposing a whole bunch of judgments about the structure of your problem. Okay? And because they're so complicated, we often aren't able to think through them all very clearly. Okay. So there's an interesting observation made recently by Andrew Gelman, which I'm sure has been made before, but it's that GP hyperparameters are not necessarily identifiable even asymptotically. Okay, so you can have an infinite amount of data and still not learn these parameters, for example. So, for example, if we had a Gaussian process on 0 to 1, okay, and it had this covariance function, so an exponential covariance function, okay, and then we've got a variance and a length scale, okay, then even as we get infinite amounts of data, we can't determine sigma squared or kappa. Okay, we can only determine sigma squared times kappa. Okay, and there's all kinds of things like this that whenever you're using non-parametric infinite dimensional methods kind of appear. Okay, and often they don't appear in a very nice, easy way to spot. They kind of appear when you get some kind of conclusion you don't fully understand, or you get uncertainties that are too small. Okay, so I think we're in a situation where Gaussian processes were not used that widely till 10 or so, 15, 20 years ago. Now they're used all the time, yep, all over the place. We sell this out every year, okay, and could probably sell it out double, okay, and there are more people who just never hear about it. Yep. They're used in all sorts of fields. And you have to be careful a bit. Okay? If depending on how you're using them, okay, there are perversities with infinite dimensional things that your intuition is not really prepared for if you're used to kind of a finite dimensional parametric statistical world. So these problems can arise, you just need to be aware of them. There's also much more mundane problems that happen. So we have to estimate these hyperparameters. Okay. One, we said they're not identifiable, but also we've got the problem of living in a computational world where we've got to do optimization. Okay, and the optimization is just tricky. Yeah, as you'll see. You can start the optimizer 10 times and get 10 different answers. That's quite common, yeah, from 10 different points. So we can often fail to converge or get stuck in local minima. So an example I like to play with, I've got the GPy code. Okay, if we have data that looks like this, just from a sine wave, okay, so 10 data points. If I run the optimizer 10 times, okay, 9 times out of 10, I'll get a Gaussian process that looks like the sine wave I use to generate the data. Okay, 1 time in 10, I'll get this. Okay, because when we look at the likelihood of these two things, okay, they're very similar. They are almost as good explanations of the data. Okay? This is an explanation that goes up and down like this, smoothly. Okay? This is an explanation that says, well, it's just a constant with noise. Okay? And you know, when you estimate the parameters, the difference in the fitted models here and here is not that great. Okay? Because it's not that great, you can quite easily find this one by mistake. And I'm sure there are some situations where this would be a better model than this. Yeah? And in 1D, that's fine, we can look at it, okay? When you've got 30 input dimensions, it becomes really hard to spot these things, okay? So you just need to check and be careful. So, although they seem like magic when you start working them, because they fit all these wonderful things, okay, you have to do post hoc checks, yeah? To have some test data that you've held back. Can your model predict that test data? Yeah? Otherwise, you risk finding you've done all your scientific conclusions using a model like this, okay? Where you may well just have had a zero mean plus a Gaussian term, okay? But it's taken you 3 years instead. Okay. So there are various fixtures to this, okay? So one is just to run the optimizer multiple times from different start points. The next is kind of cheat in some sense. It's not cheating, it's kind of pragmatic. Yeah? We use prior distributions and things. Okay? So I've got a noise term here. I might say the noise term has got to be small. Yeah? It's got to be a small noise term. Put a prior distribution on, or constrain the noise term to be small. Okay? Or fix the hyperparameters. Yeah? Add white noise, etc. Okay? So a lot of GPs, although the code is very easy to use and jump into, okay, a lot of the kind of skill of using them is learning the right fixes to avoid this kind of thing and spotting this kind of thing. Okay? How do we constrain the models so that we get models we like? Okay, and we'll do some of that in the lab sessions. Okay. Okay. Any questions?
I have a question about the parameter optimization. Since you said that the log likelihood can be trashed in many local optima, why don't you use population-based optimizer like evolutionary optimization or something else than gradient, which can be easily trashed in local optima?
Yeah, you could do, people have, and you know the best thing to do here would be to use some sort of Monte Carlo scheme to average across all the possible hyperparameters so that this gets included in your prediction but gets down weighted. Yeah? But you can do population optimization. The problem is there's a cost to doing Gaussian processes. Okay? Every time you fit them, you have to, every time you evaluate the likelihood, it costs n cubed, the complexity, okay, where n's the number of data points. So if you have 100 data points, population-based optimizers would be fine. If you have 10,000 data points, okay, and you've got to invert a 10,000 by 10,000 matrix 1,000,000 times, you're soon going to get bored of waiting. Yeah. So there are things you could do, okay, and there are ways of making Gaussian processes cheaper that you'll see tomorrow, where to reduce the cost. But that's generally the problem. The cost of doing it means that we take these shortcuts. Any other questions?
You skipped over a slide where it talks about the difficulties in estimating the prediction error because the actual expression didn't involve some particular, it didn't involve the thing you were trying to predict, right, or the new point. I mean, that seems to me like quite a big flaw in using Gaussian processes, given that you want to put some probabilistic interpretation on the values of things. I mean, how do you get around that?
So just.
Is that just a particular example?
So could you say the question louder and repeat it for me? I mean, because.
Yeah. So can we go back to the slide where you talked about uncertainty and the problem of.
Yep. This one.
This one here. Okay. So you're trying to determine the variance of a prediction as a new data point. Okay. And the problem here is that Okay, the posterior variance does not depend on y. So what is y here? This is the new.
So this is, we got a board rubber. So we've got x and y, yep, and I'm saying our training data are the observed values of y and the locations at which they were. Yeah. Okay. And this prediction of the variance doesn't directly depend upon y. Okay. But there is some hidden dependence because these covariance functions have hyperparameters, and the hyperparameters were estimated using a log likelihood that did include y. And so y is used to learn like the length scale and so on, but it doesn't directly appear in here.
Okay. Because, for example, if we were to choose the exponentiated quadratic, the hyperparameters there would have been chosen through some
Yeah.
that involved okay.
Yeah. So the question was if we use an exponential quadratic, the length scale would be chosen on the basis of x and y here. Yeah. Okay. Yeah.
One way of dealing with this would be determining the mean function in advance. Is that correct?
It might do. So that's what we tend to do in practice, right? So you can. I said before, if you had a mean function. Oh, I'm going the wrong way. Okay. If you had a mean function that depended on unknown parameters, beta, you could integrate them out. Yep. In practice, we tend not to do that because you get these problems of finding the wrong bit of space. So in practice, what we tend to do is fit a mean function first, subtract that from the data, and then fit a Gaussian process to the residual. Okay? The machine learners would never do that, and Neil would be shouting at me if he was in the room. Okay? He hates the kind of parametric aspect of it. The reason we do it in the field I work in, uncertainty quantification, is because we're often extrapolating. We don't have huge amounts of data. Yeah? If you have millions of data points throughout all the bits of space, don't bother with the mean function, have it at 0. Yeah? But if you're really extrapolating or interpolating large distances, then a mean function can really help. Yeah.
That sort of like the last thing you said, you're just flying outside.
Yeah. A large data set in high dimensions, even, you're always interpolating a long way. Yeah. Is there food here yet? I'll keep talking. Okay. Any other questions? Okay. So what I thought I'd do, just briefly, okay, is just talk about some of the applications of Gaussian processes in the field I work in, which is uncertainty quantification. Okay. So uncertainty quantification is how do we do statistics with computer models. Okay. So classical statistics was all things like linear models, okay, means and variances. Okay. But suppose you're working with an oil company, okay, and they want to either figure out how to extract more oil or where to bury the carbon dioxide, for example, is the problem I work on, carbon capture and storage. Yeah? So they've got complex models that describe the geology they're working in, okay, and how fluid will flow in it. Okay? And those complex simulation models, they've spent probably millions of pounds developing, okay, over decades. Yeah? And those models might take hours to run or weeks to run. Yeah? And they want to use those models to better do whatever it is they do. Yeah? We can't use classical statistics, things like Monte Carlo, anymore. Okay. What can we do? Or climate science. Yeah? We're talking about reorganizing the world economy, okay, on the basis of predictions from a climate model, a computer model, yeah? And some physics. Yeah? The greenhouse gases are physics, all the rest is encoded in these complex simulation models. Okay? So they simulate the oceans, the atmosphere, the clouds, the plants, the ice sheets, so on. Okay? And they want to make predictions on the basis of these models. Okay? So the problem is here, how do we do all the things we do in statistics and machine learning, okay, with these complex models? Yeah? Things like replication, randomization, etc., make no sense for computer models. Yeah? We've just got a complex model we want to run. Okay? So how do we make inferences from this simulation? So there's questions like, how do we estimate parameters? Yeah? How do we relate simulators to reality? Yeah, how do we make uncertainty statements? If you're Galileo dropping a ball off the Leaning Tower of Pisa, yeah, and you want to learn something about gravity, you could do it 10 times and get 10 different measurements of this ball falling. Yeah? And that gives you uncertainty about the gravitational acceleration. Yeah? If you're doing it on a computer, there's no uncertainty there. It's deterministic. Yeah? How do we add in uncertainty in the right place to make meaningful uncertainty statements about the world? Okay. So the idea is very simple. Yeah, we think of the simulator as a function that maps from inputs to outputs. Okay, both will be some subsets of Rn. Okay, some Euclidean space typically. Okay, doesn't need to be. And the problem is, for slow simulators, we can only do this a small number of times. Oh, I've changed notation. Okay, we can only run the simulator at a small number of locations, a small number of inputs. Okay, and we know the output at a small number of outputs. And we've got to do all our judgments on the basis of 10 runs of the model, 1,000 runs of the model. Okay, so for the IPCC, the Intergovernmental Panel on Climate Change, okay, there is a UN body that writes a report every 5 or 6 years, okay, about the future of the world climate, okay, and makes recommendations to governments. They typically ask each modelling centre, so that's about 8 centres, to make a prediction. Yep, for a number of scenarios. And each of these lines, so this is the UK one, this is 2 US ones, there's a Japanese one, there's a French one. So each of these lines takes 3 months to run on a supercomputer. Yep. And they're getting better with uncertainty. They're starting to put small ranges around these things. They might do 6 runs of each model now, okay, slightly vary things. But how do we do meaningful predictions about what's going to happen to the temperature in 2100 for these huge models that take 3 months to run? Okay, so the idea that's taken hold is to use Gaussian processors. Okay, so the idea is if the simulator is expensive, if your computer model is expensive, we're going to build a cheap model of it, an approximation of it. So this is going to be a model of the scientist's model, if you like. Okay, so the scientist has their simulator. We're going to build what we call an emulator or a surrogate model of it. And the idea is that the emulator or surrogate will approximate the simulator in some way. And then we're going to try and do all our inference using the emulator rather than the simulator. Okay. So as you might expect, Gaussian processors are the main way that I do this. Okay, and the main way the community does this. Okay. People do use things like linear regression on neural networks, but Gaussian processors overwhelmingly are the main tool used in the UQ field in situations where you have a small number of model runs. Okay, at least in statistical UQ. There's a applied math UQ where they do slightly different things. Okay. Okay, so I don't really want to say too much, but I'll just give some examples of why Gaussian processors are useful. Okay, so this was a simple example where published a couple of years ago, where we're trying to predict precipitation patterns around the globe. Okay, so these are a picture of what precipitation does around the globe. Okay? And we're doing it as a function of the astronomical parameters, which is how the Earth's orbit varies as it goes around the sun. Okay? So the Earth's tilted on an axis, it goes around the sun. Okay? And the tilt changes on about an 80,000 year time scale. Okay? It also precesses, because gyroscopes precess. Okay, and it also processes another way when it gets closer to the Earth. Okay, so these are these 3 parameters. Okay, and the scientists have done a very careful thing where they'd started with linear regression. Okay, so they're doing linear regression to try and predict this pattern from these things. Okay, and they got a so-so accuracy of 63%. Okay, but then they started thinking much harder, and we're using like trigonometric terms and have built all kinds of complex boutique kind of features into their linear regression. Okay, they spent a bit of time doing this. So we tried it with a GP, just kind of straight out the box, no thinking at all. Okay, and it beat the effort that they'd spent a lot of time working on. Okay, and it's for this reason, this non-parametric reason we said before. Okay, here you can put lots of time in thinking about trigonometric terms and particular features. Okay, but Gaussian processors or other non-parametric methods, okay, they are these infinite dimensional models that have all kinds of features, okay, and often they can just pick out the right kind of features to use. Okay, so here was a very kind of simple win where we beat kind of parametric models with no effort. Okay, and there's other things we could do. This is an example where we're trying to predict gas laws. Okay, so gas laws sound like things Boyle was doing, or Hooke, or whoever it was doing it two centuries ago. Okay, but they're still important for industrial processes. So for carbon capture and storage, you need to know how the carbon dioxide is going to behave when you pump it under various conditions back into the aquifers where you're going to bury it. Okay. And we've got measurements. See, this is a crappy plot. Okay, you've got some measurements. Okay, but then you've got loads of uncertainty about things. But the thermodynamicists are very clever. Okay, they know there are physical laws that it must obey. They know the derivatives of this relationship are zero in places. Okay, they know the integral in the place where we have no data is zero. Okay? And so what we're able to do is to build a Gaussian process that fits to the data, okay, but also build in this physical structure. Okay? And this is really key here. Okay? Just fitting to these data points gave us something, but no one really trusted it. There's no reason at all to trust it. But by building in the physics, we're able to get something that not only fits the data, and it's still a Gaussian process that's nice and easy to work with, okay, but it obeys the laws of thermodynamics. Okay, and that's kind of one of the advantages of GPs.
How are those built in? Can you just be briefly described?
Yeah, of course. Okay. That should take me to lunch. It looks like it's arriving. Stop. So we said that if f was a Gaussian process, okay, then so this is some mean function, and so some covariance function, and let's just apply a linear operator. So let's just pick a particular linear operator. Okay. So let's have df by dx. Okay, so we're going to differentiate f. Okay, then this is still a Gaussian process. Okay, but now it has mean function that we just differentiated it. Okay, I'm just going to slightly use notation, and the covariance function is going to be d2x dx prime k x prime. Okay, it's very simple basically. So you just differentiate your mean function, which is 0 here. Okay, so that's still 0, and then the covariance function. So RBF, say, it's easily differentiable. You just differentiate it once in each of the two arguments, and then all I do is I condition my Gaussian process on the observations I have. You know, these things, okay, and the fact that df by dx is 0 at, you know, x1 or whatever. Okay. Because jointly, I should also say, space f and df by dx are jointly a Gaussian process. Yep. So I can just build in whatever information I like. Okay. So we've just got a grant looking at extending this a bit further, actually. So for trying to get physically obedient GPs. Okay. So in many situations, you have, let's say, fluid flow problems. Okay. You've got a whole bunch of laws that you know the situation behaves, and you can solve these PDEs in various ways. Okay? But there are some PDEs that are simpler than others. Okay? So, for example, you might know it is an incompressible field, yeah, or an irrotational field, yeah. Things or, you know, conservative mass is conserved, yeah, and you might want your approximation model to do that. Okay? So there are ways of extending Gaussian processes so that any linear constraint is obeyed. So if you've got a linear set of PDEs that applies to your model, okay, and you want your Gaussian process to still obey those linear PDEs, we can do that. Okay, so there's a very nice paper by Jidling et al. Appeared in the machine learning lecture last year, and so we're going to try and use that basically. Okay. Oh, food has arrived, look. Okay, so I'm going to shut up because I've been talking forever. So all I was going to say is that, you know, GPs once were kind of these the best china in this phrase here, that brought out by specialists or on rare occasions. Okay, they're now kind of ubiquitous. When I started working on them in my postdoc about 10 years ago, okay, not many people work with them. Now, nearly everyone has played with them at some point within statistics and machine learning. Okay. And they're popular for all the reasons I said. You know, they're mathematically tractable, that's the main reason, and they're kind of inherently natural, I think, ways. And finally, I guess they've just been used so widely now. We've got a big body of empirical success across all kinds of disciplines where they've been used successfully to make better predictions or make better inferences. Okay, lunchtime.
Thank you, Richard. So we're having lunch now. For 2, we're going to have the lab. So the lab notebooks already, the first one is already on the web.